Haas, who's currently at Tel Aviv University and Cornell Tech. We will talk about Kolmogorov complexity and cryptography. Just want to take the occasion to congratulate Rafael for the very recent amazing news that he's an ACM fellow.
We good to start?
I think so. 9:32.
So let me just. So hi everyone, welcome to this third day on cryptography, and it's really fun to be here and in particular talk about this topic that Yanni and I have been working on for the last few years, and we're both new to Kolmogorov complexity and meta complexity, and it just turns out that there are so many amazing connections between the fields of cryptography and Kolmogorov complexity, and I hope that there will be many, many more. So since I assume most of you are not cryptographers, my plan will be to start off by giving you a very quick review of what's been happening in cryptography for the last 2000 years. And then we'll move on to some more recent results. So cryptography for the last few thousand years it really was in a dark time, what I refer to as the dark ages of cryptography. And roughly speaking, the way crypto proceeded was as follows. We would have somebody who invented some scheme, typically it was for encryption, and maybe claim that known attacks on these encryption schemes fail. They maybe manage to even argue this, that known attacks don't work. Then we employ a scheme, often in very critical situations, often in military applications. And of course, after some time, given how important these applications were, the scheme was broken. At that point, we have to go back here, come up with a new scheme. Often it was a patch. At some point, there was a revolution. We have to really come up with a new paradigm. And it went on and on like that. And this is really how things proceeded up until maybe the 50s, when Shannon tried to get a scientific foundation for cryptography. And the real revolution came in the work of Diffie-Hellman from 1976. Incidentally, is also the year I was born. When they came up with this notion of what is today called a one-way function. In fact, they already called it that in their original paper. This paper, which starts off with a humble first line, we're on the brink of a revolution in cryptography. You know, they were right. Okay, so what is a one-way function? As you know, a one-way function is a function that is easy to compute. So given an input x, typically think of this as a random string. It's easy to compute a function to get f of x. But given f of x, it's hard to go back. When we say hard to go back would mean there's no polynomial time algorithm that given f of x can compute the pre-image x. And easy means it can be computed in polynomial time. The most typical example of a candidate one-way function is multiplication. So multiplying two large numbers is easy, but if I ask you to factor the multiplication of two large numbers, that is somewhat hard. And if they're primes, we believe it's very hard. So the formal definition is as follows. We're looking for a function f that is polynomial time computable. And we say it's one way if for every probabilistic polynomial time attacker A, there exists a negligible function such that if I sample a random x, apply the function, give the output to the attacker, the probability that he's able to find a pre-image, any pre-image, should be negligible. So very small. In crypto, we sometimes use the notion of uniform algorithms, PPT, probabilistic polynomial time algorithms, sometimes non-uniform circuits. For basically any of the results or none of the results that I'm going to talk about today, this will actually make a difference. So I'm going to stick to PPT, but it really works for non-uniform PPT also. And typically, it's easier to prove things for non-uniform PPT. Some of the results that I will mention were first proven for non-uniform, and then later on, one could also extend it to uniform too. Okay, so why did they come up with this function? Well, this notion of a function. The intuition that they had was this is something that should be minimal for cryptography. Right? For any reasonable form of encryption scheme or any kind of applications of cryptography, we need something like one-wayness. We need it to be easy to encrypt something, but it should be hard to recover the message from the encryption. Okay, so it kind of has a flavor of one-wayness in it. And somewhat magically, it turned out actually over the years, people managed to show that their intuition was completely right. This is actually required for most of the central tasks in cryptography. Basically, everything that requires computational assumptions requires one-way functions. We have a few things that not necessarily required, actually like zero knowledge. It's not clear whether it requires it, and obfuscation. So there's a few examples of things that don't necessarily require it. But basically, everything we use on the internet today requires one-way functions. And even more magically, and this was much harder to prove, and it took many, many years to do it, one-way functions turn out to also be sufficient. So if we have one-way functions, we can get secure private key encryption scheme. That's like kind of the key killer app that we wanted. We can get pseudorandom generators, digital signatures, authentication schemes. Those are the things that we use on the internet today to communicate all the time, right? So these are things that we're running all the time on the internet. Okay, so one-way functions are necessary and sufficient to do it. So it's safe to say that whether one-way functions exist is the most important problem in cryptography. Without one-way functions, no secure communication on the internet, okay, unless quantum stuff can be done, but let's ignore that for now. The world that we live in today, everything would change, and we would not have secure communication on the internet if we don't have any one-way functions. So do we have one-way functions? Okay, before I move on, let me mention there's a bunch of things I'm not going to talk about today, but Tal will talk about in the second part of today. So there are a lot of cryptographic tasks, or a few at least, a very important one and more advanced one, they're not included, that we don't know how to get from one-way functions, like public key encryption, something called OWFs transfer, obfuscation, and so on and so forth. That's not going to be the focus of today. So we're talking about kind of these things that I will later on refer to as mini-crypt. These are the kind of central symmetry primitives in cryptography. Okay, so do we have one-way functions? As I said, we use them all the time when we communicate on the internet. So we need to get them from somewhere. And today, the way we get one-way function is we have a bunch of candidates for them. So as I mentioned, the most famous one is multiplication and the factoring-based one-way function that results from that. There's another one based on discrete log, lattice problems, and some more heuristic type constructions. These are actually the most typically used on the internet. And so far, they're all fine. They're not broken, right? And we use them. But there's always the question of time, all right? So, not broken now, but maybe somebody will break them. And there is this beautiful quote that by Joe Killian, quoting Sylvie McCulley, that cryptographers seldom sleep well at night. Why? Because we can wake up any morning and factoring has been broken and the whole internet is down. That would be pretty bad. Okay? Now, I personally think there are some spurious correlations here. It might not be the only reason why cryptographers don't sleep. There could be some self-selection here, but let's not discuss that. The point here is that things could be broken, and that would be problematic. And in fact, if quantum computers are built, then factor and discrete log would be killed off. Lattice problems, we don't know how to break them yet with a quantum computer, but they haven't been around for that long. So some of the things that we had in this crypto cycle actually survived for several hundred years, and today they can be broken like this, right? So So the central problem that we're going to be focusing on today is whether there exists some natural complexity theoretic problem that characterizes whether one-way functions exist. Does there exist some nice, clean complexity theoretic question that tells us whether one-way functions exist or not? This is not a new question. In fact, this question goes all the way back to Diff and Hellman's paper, because they were also already kind of concerned. They proposed this discrete log-based one-way function, but obviously that wasn't very satisfactory. So they actually proposed one approach towards this. And the approach was, well, they observed that if one-way functions exist, then NP cannot be equal to P. This is trivial, right? So, you know, the weakest assumption that we can use is can we get the one-way function from assumption that NP is not equal to P, or NP is not inside BPP. And that was one approach that they already proposed. This has sometimes been become referred to as the Holy Grail of cryptography, trying to prove that one-way functions exist based on just assumption, the minimal assumption NP is not inside BPP. Now, very early on, there were a few candidates based on this approach. So people tried to use NP complete problems to construct one-way functions. That actually led to constructions that often became broken using interesting techniques. So it actually led the field forward in a significant way. But very quickly, it led to a lot of skepticism. And this started already in 1979 through the work of Brassard that showed that it seems unlikely in some very specific ways to base one-way function on the assumption NP is not inside BPP. And so what Brassard showed was, in fact, if you want to go for something stronger, something called a one-way permutation, then it's actually unlikely to show this using black box reductions. So using Turing reductions, you cannot base one-way permutations on NP not inside BPP. But one-way permutation is too much. That's not a necessary condition. That's actually a much stronger object of one-way functions. So subsequently, there's been a lot of work, people trying to extend this result to one-way functions. Unfortunately, it's still wide open. So there's a bunch of very, very nice separation style results, but they don't get all the way to one-way functions. The only way to get to one-way functions is to consider even more restricted type of reductions. And if you consider real Turing reductions, in fact, none of these results go all the way. So the question is still wide open, both on getting the construction and getting a separation. Now, if this question is too hard, we can maybe try to take a more granular look at what it means to kind of base one-way function on this clean complexity theoretic assumption. And looking at Impagliazzo's worlds provides a very nice perspective. So as you've already heard in Rahul's presentation about Impagliazzo's worlds, Impagliazzo, in his very influential paper, defined a set of possible worlds that describe which kind of a complexity theoretic world we live in. Okay. So I'm going to follow kind of the same type of picture like Rafael did, where on the left, I'm stating weak assumptions, and the assumption become harder and harder. And that when we travel from left to right, we're moving through possible worlds. Okay. So on the left here, something is got messed up here in the, okay, we'll see. So on the left, we have, this is supposed to be, here we have the world where LP is inside P, MP is inside BPP. So all MP problems are easy. This is the world we call algorithmica. So in algorithmica, we can solve all MP hard problems. When we move to the right, we get eventually to the situation where MP is hard on average. And so the world heuristica is a world where NP is worst case hard, but easy on average. So in heuristic, we can solve all NP problems on average, heuristically, but it's still worst case hard. So it's a pretty decent world, right, algorithmically. Then we get to Pessyland. Here in Pessyland, NP is actually hard on average. So it's pretty shitty. We can't really use algorithms so well for everything. But unfortunately, we don't have 1A functions. Okay, so we don't have cryptography, but NP is still hard on average. And that's why it's called Pessyland. It's what Impagliazzo called the worst of all of these worlds, a very pessimistic, sad state of affairs. And then we have mini crypto, where 1A functions exist, but we don't have these stronger things like public encryption. And cryptomania is the world where we have even the strongest form of crypto, public encryption, OT. We're not going to be here. Tal is going to be there. Okay, so we're going to focus on things here. Okay. I'm going to add one extra world because every good talk needs to have a new definition. I don't have any new definitions, so I'm going to instead create a new world. So that's, so what I would like to add as a world here is a world where actually X is inside BPP. Okay, and that's what I call randomalia. It's where randomness has an unreasonable power, right? So using randomness, you can solve all of X. That's randomalia. Okay. In Impagliazzo, well, algorithmica can contain everything. So I'm going to restrict what I call algorithmica to be between randomalia and heuristica. Okay, so let's see now what the Holy Grail amounts to. The Holy Grail amounts to going from hardness of NP in the worst case to 1A functions. So that requires eliminating heuristica and Pessyland. Okay. So if I would like to prove this in the Holy Grail, I need to kill off these two worlds. I have to show that heuristica is impossible and Pessyland is impossible. So that's a pretty, lofty goal. We can also try to show something easier, to just kill off Pessyland. That means I would like to show that I can get 1A function from the assumption that NP is just hard on average, that NP contains some problem that's hard on average. And now the reason I introduced this new world was because we can also have even more loftier goal, which we need to say, look, that's nice, but what does it mean to go all the way from here? This very crazy assumption, very simple assumption, minimal assumption, X not in BPP to 1A functions. This world really should be the easiest to rule out, okay? And it's an embarrassment for all of us that nobody has managed to rule this. It's like so unreasonable that randomness would allow us exponential time speedups, but we can't rule it out. Okay, so in today's talk, what I'm going to do is to present some natural problems that characterize 1A functions, okay? And you've already heard about this in many of the previous talks. So the spoiler here, it's going to be Kolmogorov complexity style problems, okay? And that's why it's in this workshop. We're going to then use this characterization to actually elucidate exactly what it means to eliminate worlds to get 1A functions in this Impagliazzo world setting. So what I'm going to argue actually is that if you would like to understand what it means to get 1A functions and to eliminate these worlds, you really need to study meta complexity. You need to study Kolmogorov complexity. And finally, we're going to discuss a little bit about how to use cryptography. So these insights from here to actually get new insights into computational problems regarding Kolmogorov complexity. This was never our original goal, but it just like popped out on the way. Okay, so let me very, very briefly now quickly, review some of the notions that Rahul and the other Rahul mentioned. I'm going to go over them in more detail. But as you remember from the previous talks, we have this very nice Kolmogorov complexity zoo, stealing a term from the second Rahul. So we have a few different notions of Kolmogorov complexity that appeared in the literature. From the plain one, which is just an unbounded one, of where we say that the Kolmogorov complexity of a string is the length of the shortest programmed output string, to time-bounded notions. So kt, where t is in the exponent here, and we think of t as being a polynomial. is a time-bounded notion where I'm requiring the program to output the x within time t of x, t of length of x. Then we have the Levin-Kolmogorov complexity notion, where instead of bounding the running time, I'm charging for it in the cost. So I'm looking at the smallest program plus logarithm of running time. So I'm charging logarithmic in the running time. And then we have Allender's complex notion, where I'm instead adding charging for time additively. So we have a few different notions here. And there are actually even more variants. We have a conditional variant of these things, where I'm looking at conditional Kolmogorov complexity. So given a string x and some string y, what is the smallest program that outputs x given y for free?
What do you really mean in the top line instead of MKTP? What are you going to call that?
Sorry, there's no t there. Do you see a t? Let's change it quick. Or maybe not, because my computer is okay. Okay, so we have also a bunch of variants with the conditioning. And furthermore, as Rafael mentioned, there are even further variants, because I can look at either the problem K, where I'm looking at the problem of computing the Kolmogorov complexity, or a decisional version, which is this MKP or MKTP. Or even more refined, I can look at a decisional version which is parameterized by some threshold. So I'm asking, for instance, is the Kolmogorov complexity greater than n-half? And now we just need to output yes or no. So this looks kind of complicated. We have all these different notions. And indeed, the relationship, as we heard before, the relationship between them isn't really known. And so it's kind of frustrating. There's so many different notions. So what I would like to argue is actually that at least if we go to the setting of average case complexity, things become much cleaner. And we can suddenly see relationships between these notions. Some of them will turn out to be exactly the same. And some of them are very different. And there's a good reason for it. So on a high level, some of the kind of key insights that I like to draw is to characterize exactly what it means actually to take these jumps and to eliminate worlds. So let's start off with the Holy Grail. Okay, so the Holy Grail was to go from NP not inside the BPP to one-way functions. There are two characterizations of what it means to do it. The first one is going to be that you need to show that MKTP is MP complete, and you need to show worst case to average case reduction for MKTP. In order to actually to prove the Holy Grail, this is exactly what you need to do. Okay, so let's see the first direction. So let's say the MKTP is incomplete, and you have a worst case to average case reduction. So if MP is not inside P or BPP, then we know that MKTP, since it's MP complete, is also not inside BPP. If we have a worst case to average case reduction, then we also know that MKTP is average case hard. And finally, through results that we'll see later on, show that worst case hardness, average case hardness MKTP implies one-way functions. Turns out that the converse also holds. Because of this equivalence of MKTP on average with one-way functions, if you would like to go from here to here, you have to prove these two things. So method complexity is not a coincidence here. If you would like to prove the Holy Grail, you need to prove that MKTP is MP complete. So this whole vein of work that Rahul was talking about is necessary for proving the Holy Grail.
Do you actually need to prove it's NP complete under some reduction, or just that it's like not in P, assuming NP is?
Yeah, so NP complete in a non-black box way, what I mean here, right? So yes, this is kind of, it doesn't have to be through a corpuscular reduction, it has to be through some like non-black box reduction. Yeah. Now it turns out that if you change the problem to MCKTP, so this is the conditional version, this problem turns out to actually be MP complete. And so now the only thing you need to do, the only thing, is to present the worst case average case reduction for this problem. If you get a worst case average case reduction for this problem, then you've also shown the Holy Grail. And again, this is necessary. So this is exactly what you need to do. So worst case average case reduction for this problem is exactly what you need to do to get one functions from MP to ZBP. Now let's move on to the simpler problem of just ruling out epsilon. If I would like to go from average case hardness of NP to one functions, again, we can get a very clean characterization. And what it amounts to is showing that on average, the uniform distribution is the hardest for the MCKTP problem. So what I mean by this is to say, if this problem is hard for some distribution, then it's also hard for the uniform distribution. That's exactly what you need to do to rule out epsilon. And finally, we can get a similar statement for ruling out all of these worlds. And now it's in terms of the MKT little t p. So really, meta complexity is not a coincidence here. It's not just a tool that's useful. It's actually necessary. This is what we need to do in order to understand the relationships between these worlds. Okay, so as I mentioned, all of this relies on these characterizations of one-way functions using meta complexity. So, so the goal here is we'd like to find some natural problem whose average case hardness is equivalent to the existence of one-way functions, and all of these results that I mentioned here are going to follow from that. And so this was first actually achieved in a work by Levin, where he introduced this concept called a universal one-way function. So universal one-way function is a function that is one way. It's a specific function that's one way if one-way functions exist. So that is a construction that is complete for one-way functions. The only problem is that this construction is is very tailored to this exact task, not a very natural problem, right? So it's not a problem that gives much insight into whether one-way functions exist. So a few years ago, Yanni and I showed that the KT problem also has the same completeness property. So the KT problems are recalled in the time-bounded Kolmogorov complexity with respect to the uniform distribution. So looking at the uniform distribution, the simplest distribution, if this problem is hard on average, in that case, one-way functions exist, and it's an if only if. And you can also phrase it as MKTP with a threshold of n minus log m. So the decisional version with some threshold. And later on, in the last few years, there's been a bunch of other problems shown to also be equivalent, like the conditional one, like KT, the Levin one, and very recently, even just unbounded Kolmogorov complexity. And here, what's cool is that it's actually not with respect to the uniform, but with respect to any distribution. Okay, it's cool with respect to any, but there's also some negative aspects because of the fact that it's with respect to any. We'll get back to that towards that. But the point here is, right now, we actually have a bunch of different problems. In fact, basically all of the ones, almost all of the ones that in the previous slide, and they turn out to be actually equivalent with respect to the uniform distribution. So KT in this exponent, CKT, and K little t here, Levin Kolmogorov, they're all equivalent with respect to the uniform distribution, and they're equivalent to the existence of one-way functions. It's an awesome open problem, already mentioned by Rafael, whether we can get a non-meta complexity problem that characterizes one-way functions. Okay, all of these are, we have a bunch of different characterizations, but they're really, they don't behave maybe the same in the worst case, but from the outside, it's a big K here everywhere. So yeah.
What is this? Can you repeat the MKTP and in brackets n minus?
Oh, so this is the decisional version. I'm trying to decide whether Kolmogorov complexity is greater than n minus log n or smaller than n minus log n. So you don't have to compute it, just decide.
What is n? It's sublinear.
N is the length of the string.
Oh.
Actually, I'll get back to this very shortly. Now, in this complexity zoo, yeah.
Well, just want to mention that's like a before work by Hanley and Rahul, like they also showed uniform distribution over like K capital T. Allender's case, like also, it's also average case hardness is also equivalent to
No, I'll talk about that soon.
Oh,
here.
great.
So actually, it's we didn't mention all of these problems, right? There was a few problems left in this complexity zoo. In particular, Allender complexity, MKTP with the big T, where you add for running time. And this question of different thresholds. There's also space. I'm going to ignore space. But it turns out that once you go to this MKTP, the problem is actually not equivalent, but it's equivalent to something else. Turns out to actually fully characterize cryptography in NC0, one-way functions in NC0. So it's really kind of crazy how these like notions actually turn out to either some of them are the same, or in some of them characterize some other very natural primitive like one-way functions computable in NC0. So it's a beautiful work by Ren and Santaman, Raul and Hanlin, showing this. And in fact, Allender et al. Also managed to show that if you look at the conditional version, that also turns out to characterize cryptography in NC0, and that is actually NP complete. So you can now actually get a very nice characterization of exactly what it means to kind of show the super holy grail of going from NP not equal to P to cryptography in NC0. And that is, in fact, to just show a worst case to average case reduction for this problem. Okay, and one can also characterize log space one-way function using space-bounded notions, and we also had a version of this using a more ugly Kolmogorov complex notion based on space. But the conclusion here is that now we actually can see some structure into this complexity zoo, and it's almost like it's kind of crazy how these notions really turn out to really fit into the cryptographic notions.
The picture that you've showed about the Impagliazzo universe and the relation to Kolmogorov complexity variance, are these were they already known, or is this also the connection themselves are new?
Which one? No, this is like this. All these things are consequences by the characterization.
Oh, I see.
Since you can characterize one-way functions, you get these things. So now we have a very clean complexity theoretic kind of a meta-complexity interpretation of these questions of whether cryptography can be based on average case hardness or worst case hardness. And that's exactly what, it comes from here. And the final thing I wanted to mention here, I'm not going to go into this result at all, and the rest of the talk is that now let's go to this question of what happens when you change a threshold. So I said when the threshold is big, you want to decide whether Kolmogorov complexity is greater than n minus log n or smaller than n minus log n. Then we get one-way functions. What happens when you change the threshold? Actually, we don't know if this problem of MKTP becomes easier or harder. It's not a priori clear. If it's harder to decide it when the threshold is small or large. On average, we can now actually give a definitive answer. Turns out that actually when a threshold is smaller, the problem becomes a lot harder. In a very clean way. Actually, it turns out that when a threshold is small, like polylog, this will characterize sub-exponential one-way functions. When a threshold is large, we know it's only normal one-way function. And actually, it's a smooth line. It's like when you move the threshold, you get stronger and stronger down, you get stronger and stronger one-way functions. So when a threshold is, I forget, like square root, then you get quasi-polynomial one-way functions. And so it's a very clean statement that the threshold. So again, it's like mind-boggling. How can it be that this notion actually characterizes the quantitative hardness of one-way functions?
When you move the threshold down, you're saying you get a stronger hardness assumption, so the problem is easier, right? That's what you mean? Or
No.
No, the problem is hard.
The problem is harder because it's equivalent.
The threshold's polylog, like the brute force algorithm, is provably like faster than what we know when it's the thresholds again.
Yes, hardness of this is equivalent to the existence of
Hardness on
sub-exponential store one-way functions. Yeah.
Yes, that makes the problem easier. Sorry.
Yeah, I guess. Yeah. So the problem is, it's easy to break it, but it's the hardness assumption is stronger. Yeah. Sorry. Yeah, you're right. Hard and easy is very hard too.
Sorry.
Yeah. No, thank you. Yeah. Like what you should remember here is like when it's polylog, it's equivalent to sub-exponential secure body functions. So yeah.
Can you also get PRGs and then zero characterizations, or it's
so if you have one functions and then it's 0, you get automatically PRGs. But I don't think you have the full stretch, right? Like that, I don't think it's known how to get. So now that's like a purely. Now we're in a crypto regime, right? That's like now we have one functions. Let's see what we can do from that. Any other questions? Okay, so the key point here is I'm actually not going to talk about these type of things. I'm going to focus on this part here and its implications to Impagliazzo as well. And so what I'm going to do now is to show this initial result, how we characterize one functions using KT, and then kind of discuss some of the extensions to KT and actually not this, but some of the extensions. Okay, I do want to actually mention this sublinear hardness stuff, even though I won't have time to talk about it here. I think it really shows in a very beautiful way actually the connection between crypto and some of the literature in metacomplexity. In particular, these results very strongly rely on this beautiful vein of work by Oliveira and Santanaman on hardness magnification. So this is a fascinating concept or fascinating phenomenon that happens for these metacomplexity problems, where it turns out that for some of these problems, just assuming sublinear hardness for one of these metacomplexity problems, you can actually get a very strong hardness. So sublinear hardness for in particular, in our setting, it will turn out that it's actually enough to assume that the MKTP with a small threshold is hard against sublinear time to get sub-exponential one functions. Okay, and so there is a beautiful line of work on this in the metacomplexity literature. If you haven't read it, you should really look into it. Sorry?
What is OSRS?
What is which one?
The last reference.
I don't know actually. That shouldn't be there. Okay. So what we're going to talk about today now is I'll try to give you a high-level overview of this initial results and then sketch a little bit about some of the other ones. So the result we're going to show is that one-way functions exist if and only if the T-bounded Kolmogorov complexity problem is mildly hard on average. Okay. So let me now, go over in a little bit more detail this notion of Kolmogorov complexity because we kind of went over it very fast. So, as you know, the Kolmogorov complexity is a string. We define it as the length of the shortest program that outputs a string. So formally, we're fixing some Turing machine, universal Turing machine, and we're looking at the length of the shortest, what Eric called description, where the description consists of a program and some additional input, M, the W, such that M, the universal machine on M and W outputs X. This notion has lots and lots of amazing applications, but it is uncomputable. And this is why we typically consider this time-bounded notion, which is defined exactly the same way, except that the running time of the program is cut off to T on the length of the input. So think here for the remainder of the talk, think of T as being n squared. Okay. These results actually work for any T that's greater than, let's say, 1 plus epsilon n. But think of n squared for simplicity to not have to, you need to work a little bit more to work with small t. So the key question that we heard a lot about in the last few days is whether KT can be efficiently computed. Okay, so it goes back to, I wrote the 60s. We heard earlier that maybe it goes all the way back to the 50s. And it's closely related to the MCSP problem. And as Rahul mentioned yesterday, what's really cool about this problem is this parabol conjecture that goes back to the 50s or 60s that basically says there is no better algorithm for this thing than brute force search. And it's kind of like looking forward on the fact that we get this connection when it functions. Maybe it shouldn't be surprising because there are certain things in crypto for which we don't have any better attacks in brute force search. So if we want to get equivalence to crypto, we really need to start off with a problem that has such a property. Right? Whereas actually many of the candidates we have for crypto, like factoring, discrete log, and lattice problems, we do have non-trivial attacks. So it's very unlikely that they're going to be complete. So we really need to start off with a problem that has this type of character. And so it does. Or at least we believe so. Okay. Now, let me continue, since we're close to the break. Let's muse a little bit why this problem is so important. Yes, Raoul said yesterday that MCSP may be more important than SAT, and not clear who wants to sign on to that. But I would also argue that this KT problem is super fundamental. It's really much more important than just a question of complexity. This is really about the world that we live in. Okay, so what would happen if KT is easy? Okay, well, number one, we can do optimal file compression. Right, that's great. We can optimize. We can compress all files in a clean way. Very nice. But it doesn't change fundamentally what that we live in, right? I'm here very right now. I'm very hand wavy, but yes, I do mean the search version. And actually, it turns out that by this characterization, you actually have decision to search equivalence, and that's going to follow from actually the connection with cryptography. But so yes, indeed, when I talk about here, I mean the search version. What I'm giving a string C, you shouldn't just output the complexity, but also find the short program that generates this. This is what actually in the 60s they referred to as a constructive version of the Kolmogorov complexity problem. Don't just tell me what it is, but give me a witness. Okay, but something much more interesting happened. What I claim is that science becomes easy. Okay, at least if you believe Occam's razor. So what does Occam's razor say? Well, this is what it says. It's not. It's written in the short Kolmogorov complexity. Entities are not to be multiplied without necessity. So what does that mean? That means that if you have a bunch of observations, okay, and if you give me an explanation to why these observations happen, the simplest one is most likely the truest. Okay, and this is how science proceeds. Right? If we have a simple explanation to some physical observation, this is most likely what we believe to be the truest scientific theory. Now, if this is easy, then we don't need really scientists. At least, we will still need us to get the data. We'll be the slaves for the computers that will just find the best models. We will go and collect. And the computers will just do all the interesting stuff. We might still get to that with this GP3 style things, even if it's not optimal. But luckily we're not fully there yet. But if KT is easy, we're doomed. Okay, there's nothing for us to do except to collect evidence. So this is a very fundamental problem. We really need to understand it. Okay, we're going to talk about the average case hardness of this problem. And it's really fascinating when you read this Trachtenbrot's survey about what happened in the Soviet Union in the 60s. This was in the 60s, remember that was before average case hardness was considered in the, or average case complexity was considered in the complexity theory literature. Turns out that they already looked at it, okay? They didn't call it average case complexity. They looked at, for this particular question of Kolmogorov complexity, they looked at what they call the frequential version. Okay? So they asked, does there exist an algorithm that computes KT for a large fraction of x's? Okay? That's exactly the same as saying, how hard is it on the uniform distribution? Right? If you can compute it for a large fraction of inputs, that's the same thing as saying you can compute it for a high probability over the uniform distribution. And obviously, a very simple observation was made that this problem cannot be super hard, at least if you just want an approximation. Okay, so if you want to just get an approximation within, let's say, log n, then it's very easy to actually solve it with high probability. In fact, you can solve it with probability 1 minus 1 over n, so almost probability 1, by just outputting n, the length of the string. And this relies on this observation that we saw that by a very simple counting order, most strings actually have Kolmogorov complexity close to n. So if you just want to be within log n, just output n, and you're good to go. Okay, so if you look at the approximate version, you cannot assume this is very, very hard. But can you do better than 1 minus 1 over n? And that's a problem that they left open, at least according to Trachtenbrot. So can you beat this 1 over n trivial bound? I'm just boom. So that's the type of hardness assumption we're going to look at. Can you beat this trivial bound? And now we're going to use the standard notion of average case hardness in complexity theory, but this notion of mild average case hardness. So we say that a problem where a function is mildly hard on average if there exists some polynomial so that you cannot compute it with probability better than 1 minus 1 over p of n. So maybe you can do it with 1 minus 1 over n, but if you cannot do it with better probability than 1 minus 1 over n squared, then it's mildly hard on average. So there exists some polynomial, maybe it's n squared, maybe it's n cubed. Okay. So maybe this is easy for 1 minus 1 over n, but maybe it's still mildly hard on average. And we can also clearly define the same way for approximating it. That means that I should do it, I should compute a C approximation, where I'm saying C approximation, I mean within additively C. The definition clear? Okay, so we're ready now to actually formally state the theorem. So the theorem says the following things are equivalent. One, if functions exist. There exists a polynomial such that kt is mildly hard on average. And in fact, for every polynomial that's just slightly bigger than just n, the non-trivial thing, and every c, it's actually mildly hard on average to c log and approximate kt. So there's a few different corollaries you can get from this. I usually hate having more than two colors except black, but I had to do it here, so I apologize for it. It hurts my eyes, but I wanted to distinguish between these different types of corollaries. Okay, the first corollary, it's red here. It's going to be about connections between cryptography and meta complexity. So it's just the trivial corollary that one if functions exist if and only if kt is hard on average. Okay, so kt characterizes one if functions. Now, I wanted to highlight these other things, which was not something we were interested in, but just popped out, which is are interesting corollaries just for Kolmogorov complexity on its own. And so the first thing we get is the equivalence between these two things. So we get an even approximability result. If this problem is hard to compute exactly, then it's also hard to approximate within C log n. So it's a log n approximability result. These type of things were not known before. And we still don't know how to do this without going through cryptography. Like without going through. So this proof is going to, as we'll see, we'll go through a bunch of cryptographic constructions of pseudo-realm generators. We don't know how to achieve such a result. It doesn't talk about crypto at all, right? It just talks about Kolmogorov complexity without using these cryptographic techniques. Another thing is this decision to search question Ligia mentioned. So it's actually not a direct correlate of how this is stated, but it turns out that this is actually a correlate of the way it's proved. What we show is that actually, if this problem is hard to compute, that's equivalent to saying that it's actually hard to find a witness. So in other words, if you can compute kt, you can actually find a witness also, at least on average. You can find a k witness or kt witness a minimal size program that does it. Again, we don't know how to achieve these type of things without going through cryptography. And this is actually, again, a question that was already in this, as I mentioned in the Trachtenberg survey about what happened in the 60s. They call this the constructive Kolmogorov complexity problem. Are these things equivalent? And we still don't know how to do it in the worst case setting, but in the average case setting, it turned out to be equivalent.
Polynomial T is that exists in number 2.
Yeah, there exists. So basically, it doesn't matter. You know, if it's hard for some T, then it's going to be hard for all T's. Right here it says it exists some for each hard, and here you get it for all T. That again actually is not something that's trivially. I don't know. Maybe you can show that other ways also. I haven't thought of it.
The hardness of one-way function.
No, so yeah, if there exists some T, then you get a one-way function. If you get a one-way function, you can prove hardness for all T.
No, I'm saying that the polynomial itself in 2 depends on the polynomial that is, or the function, the hardness of the one-way function.
No, it turns like as I said here, because you see here you can do for any, start up with any T. If it's hard for n cubed, then you're going to show it's hard for n squared. This is actually just relies on some stupid padding arguments, those type of things, which you can do for one-way functions, but it's not clear how to do padding. Actually, so I don't know if you can do this without it, but our proof goes through one-way functions again. One-way functions are paddable, so you can rely on like trivial properties about one-way functions. But it's not clear how to do padding for KT, actually. Okay, so we're going to discuss the proof probably in the next part of the. But before going there, I'd like to just point out that we're not obviously the first to have these connections between cryptography and one-way functions. As we already heard, there's already been this connection between cryptography and Kolmogorov complexity, meta complexity. These go back to Rasberg and Rudig, Kabetz and Kai, and Allen et al., where it was shown that the existence of one-way functions imply worst case hardness of KT. Okay, so this is a one-sided direction. Shown if one-way functions exist, then KT is worst case hard. We still don't know how to go back, right? We would love to show that going from worst case hardness for KT, that implies one-way function. That would be amazing, but we still don't know it. Okay. Nevertheless, it's going to be a starting point for showing that one-way functions imply that KT is also hard on average. So we're going to start off there and have to work harder, but also show average case hardness. And I also like to point out this very nice work by Raoul from just actually a few years before ours, or 1 year before ours. Raoul actually conjectured that these things should be equivalent, at least for MCSP. And managed to show this. He showed that MCSP actually being hard on average is hard on average if and only if one-way functions exist under a new conjecture. So he presented a very nice conjecture under which these two things are equivalent. So it already kind of pointed towards that there really should exist such a connection. Okay, so now I'm going to try to give you this overview of this proof. And the real proof goes by 2 implies 1 implies 3. I'm not going to do that. I'm just going to show the easier thing of just going from 1 to 2. Then we don't have to deal with any of these like annoying padding things for running time. And so we're going to show it in 2 steps. In the first step, we're going to show that if KT is mildly hard on average, then one-way functions exist. And then we're going to show if one-way functions exist, then KT has to be hard on average. Okay, this direction actually intuitively should be the easier one. Turns out that that's the harder one to show. Okay, this is the one that we already had intuitively, right? We already knew that if we have one-way functions, we have PRGs, and PRGs can be killed off by MKTP, right? Turns out that it doesn't work so trivially here because we only have an MKTP oracle that works with high probability. And so we can actually not kill off any PAG with the MKTP oracle. That's still an open problem, actually, whether we can do that. So we'll have to work actually harder to show that KT is mildly hard on average, and not just worst case hard. This one actually is going to be very easy, and we're going to actually give you. I'm going to give you almost the whole proof of this. Okay. So I still have 2 more minutes or a few more minutes. So I actually have 4 more minutes. Okay. So I'm going to give you the construction, and we'll analyze it later, and then you will maybe have time during the break absorb the construction. Okay. So the goal here is we are showing that if KT is hard on average, we want to get a one-in function. Now, there is this very nice result by Andy Yao, one of the original key results in the foundations of cryptography, that says that to get a one-way function, we can actually, it suffices to get a weaker concept called a weak one-way function. So what's a weak one-way function? A weak one-way function is really the mild hard on average version of a one-way function. So remember, in a one-way function, it's a function where it's easy to compute, but really, really hard to go back. Right? You can only go back with very small probability. In this version, it suffices that there exists some polynomial such that you cannot go back with probability better than 1 minus 1 over p of n. So let's say, let's fix n cubed. Right? You cannot invert it better than 1 minus 1 over n cubed. And the key point is that if you have a one-way function like this, then you can use parallel repetition to get a strong one-way function. You just repeat it many times. So what we will show here is that from Kolmogorov complexity, we can get a weak one-way function, and then we can use Yao's hardness simplification theorem to get a strong one-way function. Let me already now mention one of the most important open problems here, if you would like to make this practical. Remove this step. Okay, this step is horrible in practice, because it requires you to actually repeat the function n times. And that's going to kill basically all practical efficiency. Okay, because now you need to have like an n square style construction. And so nobody's going to want to use that. So it would be really great if you could get a construction that directly becomes a strong one-way function.
What if it's strong?
No, it doesn't. Actually, it doesn't work. We still actually only. And let me mention another. If you don't care about practice of this, there's also a very important theoretical implication of why this sucks. Okay, this prevents us from even if we start off with the Peribor conjecture, we assume that MKTP is there's nothing better than brute force search. Okay, we still only get a one-way function that can be actually, it's not resilient against that, because Yao here is pretty shitty with respect to that, because now the security parameter is much larger. You start off with something n, and now you have n parallel partitions. Now it's n square length, but your security is only against 2 to the n. So you've actually not gotten like full exponential security. So this is also very important for practice, for theory. Yeah.
Just want to point out my paper was who showed that in the exponential security regime, KT corresponds to weak one function. And I believe in the same regime, weak to strong one function is a big open problem. So KT,
So you can get a weak one function with strong security. So it's equivalent. Yeah.
yes,
But
exponentially hard if I know if exponential secure weak one function.
indeed. But just because we don't know how to go from weak to strong one functions in a doesn't mean that we can't do it now going through KT directly, right? Maybe there's a direct construction, and that will allow us to, in a kind of non-black box way,
Maybe
get go from weak to strong one functions. I don't see like a reason why it shouldn't. I don't know. Okay, so we'll take a break now, and then we'll move on to discussing the construction.
Zoom at 11.